All right, so in section 5.2, we're starting off with this warm-up, and we want to fill in the first two rows of this table. After today, we should be able to get the bottom two rows. But when we have the three perpendicular bisectors of a triangle intersecting, the name of the point where they intersect we call the circumcenter. And if you have a circumcenter of a triangle, it has a special feature to us. That point is going to be equidistant to the vertices of the triangle. It means the distance from the circumcenter to each vertex is going to be equal. The next concurrent point we have is the intersection of the angle bisectors. We call that one the incenter, which also has a special feature. It's going to be equidistant, not to the vertices, but to the sides of the triangle. So those are our first two concurrent points. We have two more, and after today, we should be able to fill in the blanks for those. So keeping these straight, remembering which ones they are, is going to be something that's very significant for us. A little bit more with this warm-up. Sometimes, always, or never. Number two, the incenter is on the triangle. Well, the incenter, so here's my triangle, incenter is angle bisector, angle bisector, angle bisector. Will the incenter ever be on the triangle? And the answer to that one is going to be never. The incenter is always inside the circle, or excuse me, inside the triangle. Incenter always on the inside because these angle bisectors are always bending towards the inside. They're never going to go outside of the triangle, whether the triangle is acute, obtuse, or right. Number three, the circumcenter is outside the triangle. So think about that one for a second. Can you think of some examples where maybe I could get that circumcenter outside of the triangle? Is it sometimes, always, or never outside of the triangle? Give you a quick 5 seconds if you want to think about that. All right, so if I had an obtuse triangle like this, and I start drawing in my perpendicular bisectors, the perpendicular bisector of this bottom segment would look something kind of like this. And the perpendicular bisector of this segment would look something kind of like this as well, perpendicular and bisecting. So already it's looking like I'm on the outside of the triangle. So the circumcenter sometimes, when the triangle is obtuse, will be outside the triangle. Number four, I've kind of answered this one already. The incenter is inside the triangle. Whether the triangle is acute, obtuse, or right, that one is going to be always. And the circumcenter is on the triangle. Can you think of a scenario where the circumcenter is on the triangle? So if my triangle is a right triangle, I could do the perpendicular bisector of this side. I could do the perpendicular bisector of the bottom side, and then the perpendicular bisector of the hypotenuse. They're all going to intersect on the triangle itself. It would be actually on the hypotenuse. So this is going to be a sometimes. Location, location, location. Incenter, always inside the triangle. Circumcenter could be inside, outside, or on the triangle, depending on what kind of triangle that you have. All right, number 6, I'll go ahead and slow down here for a minute. And can you solve for these three unknowns? Suggestion number 1, can you identify what kind of point H is? Based off of those markings, H is what kind of point, and from there, can you find those unknowns? Go ahead and talk to the person sitting next to you. If you like, can you try to identify and find? Go for it. All right, so to the questions being asked and the one that wasn't asked here, point H is the incenter because it is the intersection of all three of those angle bisectors. So H is the incenter, which is significant for us in solving some of these. And I know sometimes the drawings look a little weird, but if you look at B, H to D, that does bend a little bit. That is not like B, H, and D are not all collinear with each other. So this is an angle bisector. It's not perpendicular to that opposite side going from B directly to D, just to point that out. Now, because it's the incenter, that means it's equidistant to all the sides. So since HE is 10, HD is 10, and then HF is 10 as well. HD is 10. That is one of our unknowns, so I do know that one. Another question is the length of AF. So if we look at this yellow triangle right here, it is a right triangle. We know a leg, we know the hypotenuse, which means we can use Pythagorean theorem again. If I call this length x, that would mean that x squared plus 10 squared is equal to 20 squared. Pythagorean theorem shows up a lot. If I have right angles, I have right triangles. So Pythagorean theorem in this yellow triangle, I can set that up. X squared plus 100 is equal to 400. Doing some algebra, that means x squared equals 300. X is the square root of 300 then. That will break down. Square root of 100 times the square root of 3 gives us square root of 300. The square root of 100 is 10. So x, the length of segment AF, is 10 root 3. And one thing I noticed as I was looking at different people working on these is there are some congruent triangles. This yellow triangle is congruent to this gray triangle. That's true. We could prove them congruent to each other, side angle side among other regions. It's also congruent to this blue triangle. That's true. It's also congruent to this green triangle. So when we're asked for the length of DA, DA is going to be equal to the same thing as X, which is that 10 root 3. Again, plenty of information, whether it's angle, angle, side. We could use hypotenuse leg because these legs are congruent. They share the hypotenuse. The green and yellow triangles are definitely congruent, so AD is the same thing. So a little bit of review from yesterday with the incenter and then talking about the circumcenter as well. Today we get into the next few concurrent points. And the first one deals with the medians of a triangle. In math, statistics, the mean, the median, and the mode. The mean we generally consider to be the average. The mode is the most often. What is the median? List of numbers, what is the median? How do we calculate it? How do we find that? That would be the mode. The mode is the most frequent. Eli? Right in the middle, yep. He said, like, if you order all the numbers, there's 3 numbers, it's the one that's going to be right in the middle. Median is the middle. If you're driving down Randall Road right in front of the Geneva Commons, you're going in different directions. In the middle, there's that grassy strip. We call that the median. The median is the middle. So the median of a triangle, going through the middle of a triangle, to be more specific, it is a segment that has endpoints at a vertex and midpoint of opposite side. That is a median. So it's not an angle bisector. It's not bisecting the angle. It's not a perpendicular bisector. It's not going through the midpoint of a segment and perpendicular to it. It's going through midpoint and the opposite vertex. That is a median. Which brings us to our next point, which is called the centroid. Great name, centroid. It has a part center in it, kind of. Centroid. It's formed by the intersection of the medians, and it has a special property. It's not equidistant to the vertex. It's not equidistant to the sides, because those are the other ones. It has a different relationship. Exactly. So we're going to have these 2-to-1 ratios. Something is going to be twice as long as something else. And to put this into words, like I'm going to write it in words. These words can seem very confusing because there's a lot of them, but it does say it correctly. The 2-to-1 ratio is this. The distance from vertex to centroid is twice as long as, so here's our 2-to-1, 2 times bigger. Vertex to centroid is twice as long as centroid to opposite midpoint. A lot more words than just saying equidistant here or equidistant there. It is a nice property, but it's just a little harder to explain. Once we start looking at some of these examples, you'll start to pick up on it a lot better. So here is my triangle. It's an acute triangle. It looks like maybe a slightly scalene, close to equilateral, close to isosceles, but I think it is scalene. And we want to draw, first of all, our medians. So I'm going to come from this lower left-hand corner. The median goes from here to the midpoint of the opposite side. So I'm predicting it as best I can. There's my first median. Right? It goes down the middle of the triangle from vertex to midpoint of opposite side. I do not know if it's bisecting this angle. In fact, unless it is a special triangle being isosceles or equilateral, this median would be different than an angle bisector. I don't know if it's perpendicular over here. In fact, it probably isn't unless it is an isosceles or equilateral triangle. Now I'm going to come from the top vertex, draw on our next median. I'm trying to predict where I think the midpoint of the bottom side is. I think it's about right here. So my median goes from vertex to the midpoint of the opposite side. So 2 of the medians are in there. What I will tell you is with this concurrent point, if I draw on the third median, it would also intersect or pass through that point. I'm not going to draw it right now because it just makes it a little bit messier here. What I am going to do, though, is talk about this 2-to-1 ratio. So this point where they intersect is called the centroid. That is the centroid. Read through this what is special part again. So then as you look at this red segment, as you look at this red median, we have a 2-to-1 ratio there. And it should look mostly accurate. My drawings aren't always drawn to scale very well, but for this one, I can see that one side is bigger than the other. In fact, this part is twice as long as that part. Vertex to centroid is twice as long as centroid to midpoint. That's the 2-to-1 ratio. If I look at the blue one, there's also a 2-to-1 ratio. If I called this 2y, this would be y. 2-to-1 ratios. Blended in with the 2-to-1 ratios, do you see a 2-to-3 ratio in here? Because sometimes based off of the parts that we're given, what we know, we might want to use a 2-to-3 ratio. Specifically, this yellow segment is 2/3 of what? 2/3 of what? Wouldn't it be 2/3 of that entire length? It's 2x over 3x. That would be our 2-to-3 ratio. Do you see a 1-to-3 ratio in there? Turn to your neighbor real quick. Where do you see a 1-to-3 ratio? So this is 1x, this is 3x. So there's a 1-to-3 ratio. Again, depending on what you have, you might not always just use a 2-to-1 ratio. You might use a variation of it because of the 2-to-1 ratio. So there's what we have. And again, I could draw in my third median, starting at this vertex, going to the midpoint of the opposite side, you have another 2-to-1 ratio. So centroid, intersection of medians, we have 2-to-1 ratios. Fourth and final one deals with the altitudes. If you've been up in an airplane, if you've climbed a mountain, you talk about the altitude. Altitude is the height. How do we measure the height of something? Do we measure it slanted? No, we go straight up and down. And altitude has to do something with perpendicular. The segment called the altitude is a segment that has endpoint at a vertex and is perpendicular to a line containing the opposite side. Segment that has endpoint at a vertex and is perpendicular to a line containing the opposite side. And this definition has some words in it that might seem like they're a little bit extra and unnecessary. We'll see why they're in here in just a moment. I didn't just say from vertex to perpendicular to the opposite side. I said a line containing the opposite side. And this is our fourth and final one. Then we'll start looking at ways to keep track of them, remember which is which, differentiate between them, and be able to identify, because that is a skill in and of itself. So altitude, perpendicular. The altitudes are the segments. The point is called the orthocenter. The orthocenter is formed by the altitudes of a triangle all intersect at the orthocenter. And what is special about it? It's where the altitudes all intersect, but it doesn't have any special features like the other ones. It's just kind of lame compared to the other ones. It's there. We can find it. We can use it. The best I can say is it creates right triangles. Because you have right triangles, then you can use Pythagorean theorem, but that isn't really special. That's just how we can solve different problems involving the orthocenter. All right, for a drawing, here's our triangle, another scalene triangle that looks acute. From the top vertex, I'm going to draw in the first altitude. I know my definition, I said it was a segment. It could be a line or array. That actually doesn't matter. I'm extending my segment kind of far here. I could turn it into array if I wanted to. There is my first altitude. Goes from vertex and is perpendicular to the opposite side. Notice it does not hit the midpoint of this bottom segment because it is not the perpendicular bisector. I'm going to change to red. Do the altitude coming from this vertex. So from this lower left vertex, I want to draw so that I'm perpendicular to the opposite side. There's my second altitude. And then my third altitude is going to come from the lower right-hand corner. I want to go perpendicular to the opposite side. Those three should all intersect. And that gives us the orthocenter. So again, the orthocenter doesn't have any great properties. We could say it makes right triangles. It's where the altitudes intersect. It is located on what's called the Euler line. Like this is the orthocenter. If we did on this exact same triangle when we found the centroid, maybe the centroid is like right there. And I also found the circumcenter. Maybe the circumcenter is like somewhere over here. The Euler line is the line that connects those 3 points. These 3 points are actually collinear, which is in itself pretty fascinating, discovered by a mathematician named Leonard Euler. But that doesn't really, again, help us solve any problems necessarily. The orthocenter is just kind of the lame one. So we call it the Mr. Rock of the points. It's just kind of lame. Those of you having for biology or cross country know what I'm talking about. Okay, so there's our fourth and final point. Now on to examples. Scroll down a little bit. Step one, label all the sides. Label the lengths that you have. Label them as best you can with the numbers if you know what they are. A good step number two, and maybe while you're doing that simultaneously, is can you figure out what point we're dealing with, intersection of what, and then what would you call it? Which special name would you give it? So in this case, K is the intersection. What point would we call the K? And then once you know that, then look at the special features. What is the superpower for it? Can you use that to your advantage? So I'm going vertex to midpoint, vertex. Ooh, I don't really know what this one is, but then I have another vertex to midpoint. So as long as these two medians, this median and this median are both intersecting each other, that makes K the centroid. It's got to be. So this last segment, which I don't have any information about this bottom side, this blue one must be the centroid also because it goes from vertex through that centroid. As far as the numbers go, if JK is equal to 8, then, get rid of the screen. If JK is 8, turn to your neighbor. How long is KL then? This is our 2-to-1 ratio. Hope you said KL is 4. The question we have, though, is about JL. Turn back to your neighbor. How long is segment JL then? Wouldn't it be 8 plus 4, 12? We're also told that HK is equal to 3. So HK, this segment over here, is equal to 3. If I want to, I can get rid of these other ones just to make it stand out more. This is 3. Turn to your friend. How long is segment MK then? And the question is, how big is MK? Well, MK is 6. Right? Centroid, 2-to-1 ratios. Scrolling it down. Put the markings, put the numbers. Sometimes it's hard to label those numbers or those lengths when they're really overlapping with each other. I think this is one of those times where it's kind of hard to distinguish those. Got a couple of right angles in there because of the perpendicular. And AB is considered an altitude. It goes from vertex perpendicular to opposite side. CD is an altitude because it goes from a vertex and it's perpendicular to opposite side. That means that their intersection, this point that I'm filling in right now, would be considered the orthocenter. But does that even matter? Not really. I didn't even give it a name, right? There's not even a letter there. It's so insignificant that it's the orthocenter that it doesn't even warrant a name. It's just there. If I told you this was the orthocenter, then you would have known that those would have been perpendicular, and that might have helped us. But in this case, we have perpendicular, we have right angles, which means we have right triangles, so we can solve for some lengths. You want to know the length of AD. AD is inside of this yellow triangle. It's one of the sides. If I draw that yellow triangle, I know that this length is 10. That's the length of CD. I don't know the bottom, nor do I know the hypotenuse. This is AD. Bottom one, the one we want, I don't know yet. In order to use Pythagorean theorem, I need to know two things. I'll go ahead and call this one y for right now. I don't know x or y. But can you look in the diagram? Can you find another right triangle where you do know more of the sides? Turn to your friend. Can you find another right triangle? How about that blue one? Try to recreate it out here. Here's that blue triangle. What do I know about it? Well, it is a right triangle. this length is 5, this length is 12. We could figure out the hypotenuse with Pythagorean theorem again. 5 squared plus 12 squared equals hypotenuse squared. This is actually called a Pythagorean triple, where all of the sides are integers. 25 plus 144 is equal to this squared. 25 plus 144 is 169. Squared 169 means that this length is 13. So what does that 13 matter? Turn to your friend. Does this help you to finish off solving the problem? So the length of that AC is 13. Isn't that what the y is equal to? Like y, this y is 13. It was the same side in both of those triangles. It was a side in both of those triangles. So now in this yellow triangle, the x that we want, go back to Pythagorean theorem again. X squared plus 10 squared equals 13 squared. X squared plus 100 is equal to 169. X squared equals 69, so x is the square root of 69. 3 times 23, but those aren't perfect squares. We can't actually break that down at all. It has an equal sign, so I don't want to approximate and put a decimal. I want to put the exact answer, and this is the simplest radical form for it. So nowhere in this problem did the fact that these intersected at the orthocenter really ever matter. The only thing about the orthocenter that would have been helpful is if I didn't know perpendicular for those and it said that this point right here is the orthocenter, then I would have known those are perpendicular. But I didn't even need to use that. So the fact that it was the orthocenter wasn't really relevant. So when you're using, when you have a right triangle and you're using the Pythagorean theorem, a lot of you learned it as a squared plus b squared equals c squared, which is fine. The problem is, like, we still need to know where is the c value at? Where is the one that's always by itself? And what I'm going to tell you is c is always the biggest one. It's always the hypotenuse, the one across from the right angle. So how did I know how to set up these equations? I always look for the one that was across from the right angle, and that had to be by itself.